Hello, so today we are going to do this problem called binary tree pruning, which is part of Leetcode September challenge. So the problem says we get a root of a binary tree and we want to return the same tree, but for every subtree that doesn't contain 1, we want to remove it. So pretty much that, remove all subtrees that don't contain 1. So if we take a look at this example, we have this tree. We have this subtree of just one node equal to 0, doesn't contain 1, so we remove it. Now notice we can't remove this 0, right? Because it has a subtree that contains 1, which is this one here. And so what we are left with is 1, 0, 1, right? For the second example, well, this entire subtree doesn't contain 1, so we can remove it. And this smaller subtree of one node doesn't contain 1, and we are left with just this one that has 1s, right? So that's pretty much the problem. Again, if we look at this last example, we remove this subtree, because there is no 1, and so it doesn't contain value 1, and so we remove it. So that's pretty much it. Now, how do we solve it? Well, the most straightforward solution is to think of it's definitely DFS, because we want to go all the way down to the last level of the tree to see if we can find 1 or not, right? So it's definitely DFS. But one thing to notice here, actually, that is pretty important is that when do we decide to remove this one, right? It's only after seeing that all of its children don't contain 1, right? Because if there was a 1 here, we won't remove it. And so the fact that we make the decision for the node, the parent, depending on the content of the children, means we need to do some sort of post-order traversal with our DFS, right? So we need to do post-order traversal for our DFS, which means basically we will call DFS on the left and the right, the node dot left, and then the node dot right, then process current node. Okay, now what does it mean to process the node? Well, it's simply when do we decide? So if the node it's here, which is a node that doesn't have a left or right child, then we can just check the value. If the value is 1, we return the node, like in this case here. But if the value is 0, we need to return none so that it gets removed, right? So here we return none. Okay, so that means processing the node here basically is just checking if this is like a leaf node. So if not node dot left or node dot left is equal to none and not node dot right, then that means depends. If the node value is equal to 1, then we want to return the node. But if it's not equal to 1, we want to remove it, so we return none, right? But if it's not a leaf node, let's say maybe we are looking at this one, then we want to return it, alright? Then we want to return the node, so here we want to return the node otherwise. And of course, we will need our base case where if the node is none, we return none, right? So what will happen here is that you may say, why are we returning node here? Which would be a valid answer, a valid question. So let's say the node does have children. So the thing, since we do post-order traversal, is that because this is 0, we will remove this and it will be attached to none, and this will remove this and it would be, this node here would have no children because we removed both. And so we would anyway do this, enter here and check if it's equal to 1, we will return it. So if this was a 1, we will return it, but since it's a 0, we will return none to the parent. And so 1 would not have any children on the right. And so that's exactly what we want here. And so because we are doing post-order traversal, we can do just by checking if the node doesn't have any children, then we process it, right? Because if it did have only 0 children, we would have removed them by this call. And by the way, this we will need to assign, right? Because let's say node dot right, because when we return none, because the child has value 0, we want to remove it completely, which means we want to assign none here, right? And here, okay? And so that's why when we are now processing 0, it would have no left or right child, and so we will enter this processing loop here, and we will return it only if its value is 1, otherwise we will return none, right? So that's the idea here of the DFS we are doing, and it works because we are doing post-order traversal. And so here we will check if not node. This is just the normal base case of, so yeah, let's call it first our DFS on node here, and we'll do the normal traversal with base case first. So if the node we are at the end, we'll just return none because node is none. Otherwise we'll do post order here, and so which means we'll do exactly what we said here, which is assign to the left the result of traversing on the left side, and same thing for the right side, and then we will process the node here. Okay, because if at this point it has a left or a right child, that means one of its left or right subtree has a value of 1, which means we need to keep it, which means we need to return none. Node here, which means we need to return node. So if this condition is not valid, that means the left or the right child, the right subtree, one of them had a 1 in it, which means the node, we need to keep the node, and so we return the node, right? And that's pretty much it. If we run this, okay, we need to call our DFS function, sorry. So here we need to call it with root and return that. And that's pretty much it, so let's submit. And that passes test cases. And this is like linear in terms of the number of nodes, and we will call it for for every node in the tree. And you could also think of it as O of H, the height of the tree, because if you want to be precise. Yeah, so that's pretty much it for this problem. Please like and subscribe, and see you on the next one. Bye.